Mesdames et messieurs, ladies and gentlemen, veuillez accueillir, please welcome Dr. Robert Sutor.
Thank you very much. So we had a little dry ice here to cool down the room. It's a little bit warmer. Also, to give you an idea, as we pointed out in the video, just how cold you have to be to do quantum computing. So as it said, we get close to absolute zero. So absolute zero is where nothing moves. So if you think of atoms and electrons, everything just stands still. And we're just a tiny, tiny little bit above that in order to do quantum computing. So I'm going to tell you a little bit more about quantum computing. I'm going to motivate the problem for you. I want to tell you why we're bothering, and I want to tell you why this is really just a completely different type of computing from anything you've seen before. So I'm going to roll back to 1981. There was a historic conference back then. It was sponsored by MIT and IBM. And they were asking some very basic questions about computers. So the computers we use today, your smartphone, your laptop, the servers on the internet, we're going to call these classical computers. They go back to the 1940s. And in the early 1980s, the physicists were asking, is this the best we can do? Right? Just because we invented these binary, these digital computers, is this what computing is going to look like forever? Will they solve every type of problem? That is. Because they were beginning to get some indications that maybe, in fact, that wasn't true. That computers can do a lot, and in fact, if you look at your smartphone, there are many, many apps you can choose from, well over 2 million, probably a lot more than that. But are there certain problems that are really just intractable for traditional classical computers? So this is a photograph of Richard Feynman. He won the Nobel Prize in the 1960s. He was a physicist at Caltech. And he was a character, let's say that, somewhat eccentric. But also, if you were to number the 100 top geniuses in the history of the planet, he's probably in that list. And so in the paper he wrote up after the conference, he put this quote. And you'll see there's one word in this quote that usually isn't in a scientific paper. He said, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." And quantum mechanics was one of his areas. Quantum mechanics really goes back to about 1900. It's one of the strangest part of physics. We'll see a little bit about that. And he said that, well, look, if nature is fundamentally built on top of quantum mechanics, and it's hard to map nature, right, chemical processes, for example, to binary computers, why don't we try building a computer on quantum mechanical principles? And so from that point on, people set out to try to do exactly that. So let me pick a very simple example, one which I suspect many of you have actually observed this morning, and it's with the caffeine molecule. Very simple molecule, there it is. I'm not going to harken back to high school chemistry too much. I've got to go a little bit there. Right? And as you can see, there are carbons and hydrogens and nitrogens. There's an oxygen thrown in there. They're atoms, basically. They're protons and neutrons, and especially there are electrons. So we're talking about energy. When I first went to school, when I learned about atoms, they looked like planets with little moons going around them, right? And then we discovered, in fact, that wasn't quite the way it worked. Things were much, much more complicated. And this is the quantum mechanics of it. If you were to represent all the information about the energy in one caffeine molecule at one instant, you would need 10 to the 48th bits, zeros and ones. So that's a 1 with 48 zeros. So a million is one with 6 zeros, a billion is one with 9 zeros. So that's a big number, but how big is that? Well, scientists have estimated that the number of atoms in the Earth are roughly 10 to the 49th to 10 to the 50th. So for that one single caffeine molecule, at one instant, you would need enough bits comparable, perhaps, to 10% of the number of atoms in the Earth. We're not building computers like that, right? We don't have computers that big. We will never have computers that big. So what is the hope for using these computers we love and have used for decades to do anything more interesting with chemistry and the interesting molecules, which, by the way, we are made of, right? All these things. Is it hopeless? Well, of course, the reason why I'm mentioning this is quantum computing. The basic unit of computation in quantum computing is a qubit, and we will be able to represent exactly all that information about that caffeine molecule in 160 qubits. We're not there yet. We hope to be there within a very few number of years. But the point is, we're going from something completely and always impossible on the classical side to something which we hope, in fact, will happen in just a few years. So these are the two fundamental principles of quantum mechanics that also come into play in quantum computing. The first is called superposition. This is sometimes incorrectly said a qubit is 0 and 1 at the same time. Mathematically, it's a little bit more complicated than that. But it's still a strange idea and gives rise to some other interesting and powerful behavior. And the second is what's called entanglement. Entanglement means that if you have one particle here and a second particle, possibly millions of light years away, if you know something about this one, you know something about the other. Now, inside a quantum computer, things aren't that far apart, right? But we can use entanglement as part of the way we do computing. Quantum computers are fundamentally different from the very lowest level all the way up. They will not replace classical computers, probably for a few hundred years, but they will work together with them. They will complement each other. Quantum computers, we hope, will be used to solve the problems that, as I've described, classical computers cannot. So it's a new approach to computers, and in fact, they even look different. On the left is what we call a cryostat. You can also see two of our research scientists on the left working with one. The actual quantum computer, the bits live inside that can at the bottom. That's where it is so completely, so very, very cold. By the way, they're also beautiful machines. They're marvels of scientific advancement, but also have a tremendous amount of elegance in the engineering that has gone into creating them. On the left is a classical chip. That is the full processor for a Power 8 computer. It's not our latest chip for power. On the right is a quantum computer, a quantum device. What I've circled there is a qubit. It looks like a little rectangle, and there are lots of little squiggly things there. The squiggles, or snake-like objects, are what connect the quantum bits to the outside environment, and in some cases, to each other. So they look different, and it really is a radically new approach to how we're going to do this. Going back to 1900, and for a long, long part of its history, we were in the quantum science era. And even now, if you go back less than 10 years ago, you'll see books that say, if anyone ever actually creates a quantum computer, well, then they'll be able to do this. So we've advanced quite a bit, and we are now in this quantum-ready phase. The quantum computers we or anyone else on the planet have are too small. to do the really breakthrough work. We're going to be honest about this. IBM always tells you exactly what we've got when it comes to quantum computers, because we honestly have to set expectations correctly, because this will play out over the next few years and decades, in fact. So you should know what you're going to get and when, at least by our estimates. Now, what we want to get to is the quantum advantage phase. This is where we can say, right over here in this field, perhaps it's artificial intelligence, perhaps it's biochemistry or medicine, perhaps it's financial services. Somewhere there, we will say, we can demonstrate an actual, differentiated, significant advantage over anything we know how to do using classical computers. It's a moving target. We hope to get there in the 2020s, that is the next decade. If we're lucky, and with science, there are no guarantees, we hope in the early 2020s, but that's what we're looking at, and that's what we're going after. So the power of a quantum computer scales with the number of qubits. Every time you add 1 qubit, you double the power of a quantum computer. Going back to the classical processor, you need to double the total number of transistors to double the power. Moore's law enters into that. But you just double it with 1 qubit. And so this is truly an example of exponential growth. Now, exponential is this weird term that I think in the popular lexicon, most people just use as really, really fast. But here, we have to be a little bit more mathematically specific. And so here, what we're saying is it grows with powers of 2, which means it doubles. So if you have a 20-qubit quantum computer, a 21-qubit quantum computer is 2 times faster, and this is where the exponent increases. So our largest working prototype is 50 qubits. How much information can that represent? That's about 10 to the 15th bits, 1 with 15 zeros. That's quite a bit of information. When we get to the point, however, when we have 200 qubits, which, again, if all goes well, we will be hitting within a few years, we will be able to represent more information during computation than there are atoms in the observable universe. Now, does this sound strange? Does this sound impossible? Does it sound ridiculous? Yes, all of the above, and welcome to quantum mechanics. This is why people like Einstein had a really hard time getting his head around some of this. But this seems to be the way it's working. And we don't need 200 qubits in the long run. We need 10,000. We need 1,000 million qubits. And that's where we're going to head out. So you can imagine the computational power that we will end up with. We'll be able to simulate chemical molecules and not just little ones like caffeine. We may be able to create new life-saving drugs. We will go from drug discovery to drug computation specifically for you. If we get there, that will be more than 10 years away. We need big quantum computers. But that gives you an idea of what we're after here. We have started commercializing these, and we've done them through the IBM Q network. You can see some of our partners here and some of our hubs. So we have hubs in Japan, in the UK, in Australia, in the US. But it seems to me we're missing one country and maybe one province here. We would love to talk to someone about doing a little bit more here in Quebec. This is a very engaged community. We made real quantum computers available 2 years ago. Actual quantum computers we put on the web. Since that time, we have had over 80,000 users run 4.4 million experiments. That's quite a lot of people. We've done it through the IBM Q experience. Over 70 papers have been written, used by over 1,500 universities. This is what the most advanced quantum computation center looks like today. This is what we think it will look like tomorrow. This is serious computing. This will work with classical computing. To learn more, just search for IBM Q. You can be using real quantum computers tonight, if you'd like to. This is a very exciting time in computation. I hope you join us. Thank you.
Mesdames et messieurs, c'est maintenant l'heure du lunch. Les conférences reprendront cet après-midi.